Okay, well, hello, and we're starting Unit 3 here. This table that's at the beginning of the handout is the answers to many of the questions that will be in this unit. It's just here for you to be able to refer to. The important thing to understand about this is that the source, by source or excitation, we mean what is the energy, what kind of energy is there, and by the oscillator, we mean what is setting up the vibration. So for the voice that we already studied, the energy would be supplied by the air coming up from the lungs, and then the oscillator would be the vocal folds. Then there is a filter that shapes the spectrum. So this here, the source and the oscillator, these determine the frequency partials, like exactly which frequencies they are, if they're harmonic, okay? Then the filter, just like the vocal tract did before with the formants, this shapes the spectrum, the peaks in the spectrum. Okay, and then the radiator is where the sound comes from that we hear. And then the example is to help you know which instruments we're putting in these different instrument families. Just for pointers, mechanical reeds are those that actually have physical reeds that you insert, like clarinets, oboes, saxophones. Lip reeds is another name for brass instruments because the lips are doing the same motion essentially as the reed. Air jet will include the flute and the organ. Okay, these will be modeled as open tubes essentially for the flute and not capped organ pipes. Then we have the bowed strings, all those that you are exciting with a bow, and then pluck strings, guitar, and the ukulele, the banjo, the mandolin, and then sometimes the violin and cello if they're plucked. The struck strings is the class that the piano will be in. And then there's the percussion instruments. And then we'll talk also about electrical instruments and electromechanical instruments as we go along through this unit. It's important to remember with Unit 3 that we're taking our simple models of the mass spring, the fixed string, mass spring system, the fixed strings, the open, closed and open tubes, and then this source filter idea. And we're seeing how far that can take us to describing the acoustical properties of the different musical instruments. Okay, so from the picture that is in the text and that was shown in class. Let me just real quickly get which number that is. Thinking in particular of figures in the text, figures 33.7, 33.8, and 33.9 are what we're referring to there. They have time they have time on the horizontal axis, they have the note of the scale. So essentially the frequency, the note on the scale on the horizontal axis, and then they have the attack transient time on the vertical. And in general, larger instruments have longer attack times. So the tuba, for example, starts up here at above 60 milliseconds, whereas the trumpet, which has a higher range, kind of goes over here. So this line would be the tuba line. This line would be the trumpet line from figure 33.9. So in general, larger instruments will have longer attack times than smaller ones. It takes longer for the air to go down and back, reflect off the end instead of the standing wave in the tube, or it takes longer for the vibration to travel along the string when they are bigger instruments. And generally, higher frequencies will have a shorter attack time, because they correspond typically with shorter lengths of tubing and faster airflow. The percussion instruments will typically have an extremely short airtime or attack time, so shorter than non-percussive instruments. Okay, so this Roman number 2, refers to figure 33.10, okay, in which it shows you the level in decibels, and then it has different families, different instruments, and then it shows you like the min and the max levels that those instruments can play. So for each instrument, this end here would be like pianissimo, and then this would be like the fortissimo. Okay, and in general, the woodwinds have the smallest dynamic range, meaning variety of sound levels that they can produce and make good sounds at. Okay, and now this is the part that I wanted to focus on most here for this video. This idea of musical intervals that will result when two strings of identical wave speed are sounded. Okay, so I'm going to draw a little keyboard here for us. Okay, we'll go ahead and start on I'm just going to draw black keys. Etc. Okay, we'll just do that much, so I don't have to take all the time to draw it out. Okay, and then this would be another C up to there. Okay, all right. So we'll see if that's any help, if that's helpful at all. Okay, so the yellow keys are all C's. It's the one to the left of the two black keys, and they are 12 semitones apart. And so if you were counting that, you would count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, I'm going to erase all of those so they don't get in my way, but that's the idea. You count the white keys and the black keys. Okay, so an octave is 12 semitones, so that's how you would count it. The C here refers to the note, and then the 4 or the 5, that refers to which octave you're at. Okay. C4 is middle C on the piano. That means that C5 is 1 octave above that. And C4 is 1 octave below. Or sorry, C3. Sorry, C3 is 1 octave below C4. That means their frequency ratios have a ratio of 2 to 1. Okay. With these ratios, the important thing to remember, okay, is that if a note is higher on the keyboard, if the note is higher on the keyboard, the frequency is larger, and the length of the string or the tube that's responsible for that note is shorter. So you can always ask yourself if it's supposed to be multiplied by 2 or divide by 2. Just ask yourself, do I expect a larger number or a smaller number? Okay, so you can use some of your intuition on that one. In case you don't know, if you have not studied music before, the keys here are C, D, E, F, G, A, B, and then it starts over with C. These others can be considered as sharps or flats, but we'll just use them for counting intervals. You won't be expected to know any tricky intervals. These are the four intervals that you need to know. Very common intervals. Okay, so let's do number 5 now. Middle C, C4, has a frequency of approximately 260 hertz. So I'm going to call that FC4 in my writing here. And then the question is, what is the frequency of FC5? Okay. Well, C5 is 1 octave above C4. Okay. So then I come up here and I say, well, that means the frequency ratio is going to be 2 to 1. Okay. So the fact that it's an octave higher means that the frequency of C5 is twice the frequency of C4, which would be 2 times 260 hertz, which would be equal to 520 hertz approximately. Okay, so that's the frequency of C5. All right, and now what about G4? Okay, so for G4, our starting point is that the frequency of C5 is 260 hertz. And the frequency of G4 is what we're interested in. Okay, so then you come to the keyboard. You start at C, okay, and you count up to G. How many semitones is that? So we have 1, 2, 3, 4, 5, 6, 7. Sorry, I wasn't supposed to start on. You don't start on the note. You start in the next one. 1, 2, 3, 4, 5, 6, 7. So 7 semitones right there tells me the frequency ratio will be 3 to 2. Okay, so that means that F of G4 will be 3/2 F of C5. C4. Holy cow. That means F of G4 will be 3 divided by 2 times 260 hertz, or 390 hertz when you multiply that out on your calculator. All right, now this part here, this relationship between frequency and wavelength, the important thing is that if the frequency goes up, the wavelength lambda goes down. Okay, so they are inversely related. Okay. I want you to consider what's called a lap harp. It's kind of the easiest way to think about these next questions. Okay, you have little pegs here, and then you have strings across it like this. Okay, those are fixed strings, right? So the frequency, the fundamental frequency of the string would be the wave speed on the string divided by 2L. So the frequency will go up as the length goes down. Or shorter strings have higher frequencies. Okay. The ratios are still the same. They're just inverse. Okay, so now number 7. If one string is twice as long as another, Okay, so we have a string of length L. To be able to draw twice as long. So string of length L, and then a string of length 2L. Same V, same wave speed V. Okay. If I pluck one and then the other, what musical interval will be sounded? Okay. So because one is twice the other, the ratio is 2:1, and that would be an octave. Okay. If the length of the string changes by a factor of 2, that's an octave. If you've ever played guitar or any string instrument, if you are playing on just a single string and then you move your finger to cut the string length in half, essentially push down in the middle of the string, then you have gone up an octave when you play that sound relative to the open string. So then for two strings a fifth apart, what are going to be the ratios of the length of the shorter string to the longer string? Let's see. Okay, so we have two strings here. One's shorter and one's longer. I'm going to call them L1 and L2. And the question is, what is the ratio of the lengths? That's asking what is L1 over L2, the shorter one to the longer one. That's what it's asking. Okay. Now, the clue here is that we're talking about a fifth. So we come here to this line and we see that the ratio for a fifth is 3:2. Okay. Now we have to say, well, does that mean it's 3/2 or does that mean it's 2/3? We know that it has to be a 2 and a 3, but which is it? And now this is where you have to think, okay, that shorter strings have higher pitches. Okay. So if the shorter string is a fifth above the longer string, then it has to be 2/3 as much, because 3/2 is greater than 1. So that would be the longer option. Okay, and then in number 9, again, we're doing two strings. Okay, so we have one string that is 20 centimeters long. And then we have another string that is going to be shorter than that because it's a third above. So I know it's a shorter string. And I'm trying to figure out what is the length of that string. Okay. All right. So then I have to figure out what interval I'm talking about. I'm talking about a third. So I come up here and I see that a third is a 5:4 ratio. Okay. So a third, musical third, has a 5:4 ratio. Okay. That can also be written as, 5/4. Okay. And then you have to say, okay, that ratio of 5:4 is the same as the ratio of my two lengths, but which one goes on top? The longer string has to go on top because 5 is greater than 4. So that says L2 over L1 is 5/4. And if you rearrange this, I did that backwards. The longer one, which I called L1 in this case, which is 20 centimeters, we'll just write the number in there. 20 centimeters over the length that we're looking for has to be equal to 5/4. So I can rearrange that equation, multiply both sides by L2 and by 4 to get 4/5, 20 centimeters, which if you multiply that out would be 16 centimeters. Okay, so that's one way to think about it. If you're good, if you like the idea of ratios like that. Okay. The other one is just to say, well, the length of the shorter string, which I've called L2 here, but I'm doing short just so it's a little bit more applicable elsewhere. okay, is going to be equal to 4/5 the length of the longer string. Okay, or conversely, the length of the longer string will be 5/4 the length of the shorter string. So that's why you have to keep in mind, do I expect this string that I'm trying to find the length of to be longer or shorter? And that is how you can figure out if it's supposed to be 4/5 or 5/4. If it's supposed to be shorter with these up here, then you have to use the inverse, so that you have numbers that are less than 1. Okay. So I'll just erase that since we're looking for the shorter one. So that means that the shorter one is 4/5 of 20 centimeters, which is 16 centimeters. So these give you the ratios, but then you have to think about whether you do it as 5/4 or 4/5, depending on if you're trying to find frequencies or pitches, and if you're above on the interval or below on the interval. Just think about if you should be getting a bigger number or a smaller number. Okay. And remembering that longer strings have lower frequencies. Okay. And then this complex tone pairs, wondering which ones will sound smoothest and roughest. Let me try to draw my little keyboard again. I should have just drawn it bigger at the beginning. Okay. Okay. So these, just to review again, the names on these keys are C, D, E, F, G, A, B, C, and then it repeats. Okay. If this one right here is C4, then that means that this one here is C3, and this one here would be called C5. The number, the octave that it's in, changes on the Cs. So this would be C3, D3, E3, F3, G3, etc., A3, B3, and then C4. So the number changes on the Cs. All right. So now when you are asked about which ones are smoothest and roughest, okay, this is your key. Okay. The octaves, fifths, and sixths will sound most smooth. Semitones, which is just like one step apart, so from here to there, or sevenths, which would be from there to there, going down, or just right next to the octave, sorry, from there to there, will sound the roughest or most dissonant. Okay, so let's try to take both of those in turn. Why that is. Okay, so consonant intervals. The frequency partials, harmonic frequency partials, are, I guess you could say, widely spaced and or overlap. Okay. What do I mean by that? Oops. I mean that if this is frequency, and this is the level or the amplitude, okay, and I did a periodic signal on C3 or C4, then I would have 260 hertz would be my first line. Then the second one, thinking of fixed strings, open tubes, then I would have 520, so F1, 2F1, 3F1, etc. Pretend they're evenly spaced. hand straight. Okay. So that would be like 780. And if I add it again, then I would get 1040, etc. Okay. So that blue one would be C4 for a periodic signal with a fundamental of C4. Now, if I do C5, C5 would have its, I'm going to draw these next to each other, but pretend they're at the same frequency. C5 would have its fundamental an octave above, so a ratio of 2 to 1, and then its first partial would be twice that, and then 4 times that. So C5 and C4, or the octaves, all the partials line up. And we don't have any dissonance or roughness due to partials that are just that are within that critical band, which we'll talk about a little more in a minute. Okay, and then if we have something like a fifth, which in this case would be G4, okay, then it would be 3/2. It would be the frequency ratio from our chart above. So it would come in like here, okay, and then twice that would lie here, and then it would be halfway in between, and then it would line up. So that would be an example for G4. So fifths, the partials also line up or are far away from each other so that you don't get any roughness or beating from the basilar membrane, the critical bands of the basilar membrane. Okay, so we have to remember this all comes back to our ears and the perception of the sound and the basilar membrane. Okay, so why do some sounds sound very dissonant? Okay, so we'll put dissonance up here. Dissonance occurs when the partials of the different notes, including the fundamental, are close. And what do I mean by that? I mean that they lie within a critical band, which produces that roughness that we talked about when we talked about hearing. So again, if I draw in my C4 spectrum, and then I do, say, C sharp, okay, then that means that I've gone up just one semitone. And so then I'm very close on my frequencies, but not as close as that, what I did before, where there's these ones down here, these are just supposed to be on top of each other. Okay, but these are separated. Okay, and then if you do 2 times that, then it would get a little more separated, and 3 times that, it would get a little more separated. And then it starts to get close, but not exactly equal to the other one, and so forth. And so you have these small differences in frequency that are less than a critical band, not just at the fundamental, but all along with these upper partials. You get all of this different roughness or beating. Similarly, so that would be kind of like a C sharp 4. And then if we did a B4, then it would be like you were almost at the octave, right? And then you were almost at the octave, etc. So then you would get, again, beating because of these differences that are kind of close. Okay. So dissonance occurs when the partials are close and lie within a critical band, and then the octaves The partials align. Another thing to know about dissonance is dissonance increases at lower frequencies. So if you go down to the bottom end of the piano, more notes that are relatively close together will sound dissonant because the critical band is a larger percentage of an octave. So next time you're around a piano, just play a B and a C together at different places on the piano, or a C and a C sharp or something, and you'll be able to hear that. Okay, but that's all of the description of this. And now let's get back to the actual bold here. How will you determine which will be the smoothest and the roughest? If you are new to music notation, and this is a little different for you, this is your rule of thumb, okay? Number one, if the note is the same, but the number is different, then that is consonant. That's your most consonant interval. Okay. Okay, your other rule of thumb is if the notes, the two notes, the names of the notes are close alphabetically, okay, then it's very dissonant. Okay. And then number three, beyond that, if they are if they are a fifth, you can check the interval. If those two rules of thumb don't give you the answer, then you can check the interval by counting semitones. Okay. So let's do these cases that are right here. I'm getting quite a bit of a mess here, but let's do it anyway. E3 to A3. So here is E3, and here is A3. So let's count. That would be one. Oh, no, you don't start on that. You go up one. Here we go. 1, 2, 3, 4, 5. So there are 5 semitones. So you say, what interval is that? Okay, 5 semitones would be a fourth right here. Okay. And so that would be a fourth. And that would be smooth, relatively smooth. You can say smoothish if you want. And then if we have E3 and F3, so which are again E3 and F3, those are only 1 semitone apart. And so that would be very dissonant. So you'll have lists, and you'll have to go on the list. Which of these would be the most consonant? Which of these would be the most dissonant? So unison, octaves, fifths, and sixths are the most consonants. The most dissonant are the semitones, so just one step on the piano, and sevenths, which are one step below the octave. Okay. All right, well, hopefully that helps. We will keep practicing with these as we go through the music section. Good luck.